All right, so welcome back to our off-season programming training. We're at week 3. Today we're going to be doing a couple of different things, but our primary focus is learning how to aim using a Limelight. So let's look at where we are right now. So we're already halfway through, and after today we'll actually be 3/4 of the way through. Next week we've got some exciting stuff. Yeah, we're already here. Okay, so yeah, next week we've got some exciting stuff, but for right now, we're getting started with our Limelight stuff. So first let's talk about what a Limelight actually is. So a Limelight is a camera in a box with a computer. You could, for vision targets in FRC, there's lots of times we have to aim at certain things on the field. You could put a Raspberry Pi or some other computer together with a custom webcam. You could do that, and you could write your own software, and you could put that on the robot. But the Limelight makes this a lot more accessible to a lot of different teams and people. Since it's a small box and it just fits right on the robot, you just have to mount it somewhere. So it can do lots of different types of things, but its primary job is using retroreflective tape. So that's a type of tape. We have some on the table over there that reflects light back in the same direction that it came in. So that means these are LEDs. These LEDs on the Limelight right here, they shine green light out, it bounces right back, and it highlights the targets more so than they would otherwise. So here's an example of what it looks like for a robot to aim using the Limelight. So that up there, that hexagon, was the target, specifically that silver-like tape at the bottom. That's what it's seeing and it's aiming at automatically. And then the green light around it is all the excess light coming off of the Limelight that's not reflecting off of retroreflective tape. So next we're actually going to see how this system works. So the foundation of what you just saw is something called PID control. So this is kind of a fancy word for something that's not actually super complex. Basically, it allows us to minimize error. So in a case like that, our robot is looking at the target. Maybe the target's over here. So there's going to be some error, maybe 10 degrees or something like that. What it allows us to do is go from where we are right now to our target by looking at how far off we are right now. It involves a couple of different terms, and we're going to look at those in a second, but this is useful for a lot of different things. For one, position control, that's what we're doing today, like controlling an angle or distance. But you can actually also use it to drive the motors on your drivetrain, to set them to a specific speed to account for things like friction or any kind of variation that might happen, any error that you want to minimize. So first we're going to talk about the proportional term. So the proportional term is the most simple, but also the foundation of PID control. And today that's actually all you're going to be doing, is using the proportional term. So all it does is it takes the error, maybe it's 10 degrees. Okay. It takes the error, maybe it's 10 degrees or so, and it multiplies it by some number. So if it's 10 degrees and our p value, or sometimes called kp, is 0.01, what we would do is multiply those two things together, and we would get 0.1, or 10% output. If you've done this before, you would know that setting your motor to 0.1 is 10% output. So initially, we're 10 degrees off, right? We correct for that at a certain speed. And as we get closer, the error decreases, right? Maybe now it's 5 degrees off. So we multiply that by 0.01 again, and suddenly we have a smaller output than we had before. So the idea is, rather than going at a constant speed, the amount that we try to get there with is less. So we put less power into it to try to get there at like a smooth, slower rate. And what you see right here is this is what happens if there's a large p-value. We get some oscillation back and forth, and it never really settles down. So next is going to be the integral term. This, again, another fancy word for something that's not actually very complex. Basically what it does is it stores the total error over time. So maybe we're originally 10 degrees off, then we correct for it, now we're 5 degrees, now we correct for it again, now we're 3 degrees off. The total of that would be 18 degrees. So rather than multiplying by the current error, this term multiplies by the total error. So that's useful in some situations if you can't quite reach your goal. Maybe you're a little bit off. Maybe there's something fighting against what you're trying to do, like friction or something like that, and you need a little bit of push to get you over the edge because it's not really getting there. The integral term can be helpful with that because over time it keeps growing even if you're staying still. So you'll eventually get to your target. But if it's too high, you can actually make the problem worse. So this is typically used sparingly. And then the final term is actually quite useful, and this is called the derivative term. So rather than the proportional term, which is multiplied again by the current error, the derivative is multiplied by the rate of change of the error. So if our error was originally 10 degrees, now we're 5 degrees off, so we're getting closer, then our rate of change would be negative 5 degrees per second if we measured it once per second. So it would be multiplied by the current rate of change. What that does is it allows us to dampen our results. So to prevent that kind of oscillation that you saw before. So in a second, you're going to see this flatten out, get a lot closer to the kind of curve that we're looking for, where it quickly gets to its target. That's by increasing that d value. Now that's, again, not really something you need to do today because your problem's pretty simple, but that is one thing that you can tune to make something work better. And the final one that we're going to look at is something called feed forward. So this is something that's quite often ignored, especially in FRC. Everyone always jumps right to PID control and often don't even understand what feed forward is. So feed forward, if PID is based on something called feedback, where we look at the current error in the system and try to correct for the error, the feed forward is based on an understanding of the system. So rather than having sensors, you're basing it on how well you understand how the system works. So, for example, a flywheel shooter where we're trying to shoot a ball, if you understand how that works, you can understand that applying a certain voltage will give you a certain output speed. And if you find the relationship there, that can help you get most of the way. So rather than having to do all of the work with the PID, it helps reduce the amount of effort that you have to put into that. Now, in our case, we're doing something quite simple. There's not really a huge application for feed forward. One of the things that we will have to look at on this is friction, right? Friction applies to our robot, friction applies to lots of things in our lives, but in particular to our robot, the friction is pretty important because if you are this far off in terms of angle from where you're trying to face, right, you're maybe just a little bit off. Friction, you might be turning so slowly to try to get to that target point that you can't even overcome the friction needed to get there. So feed forward allows you to just add something on to make it just a little bit easier for the robot to adjust there, to just barely overcome friction so that it doesn't have to worry about doing that. Another application for feed forward would be this arm, right? This arm has to work against gravity. So in order for it to lift up, right, it has to apply more voltage, and in order for it to go down, it has to apply less voltage than it would expect because of the effects of gravity, right? So a feed forward that understands how gravity affects the arm can help you negate those effects automatically so that the PID can think of it almost like it's in zero gravity. Overall, though, this is just something that's often not thought about, and it can make your job a lot easier when you're trying to make a system work well. So this is a very quick slide, but if you know calculus or you're familiar with these concepts, you can come back later to look at this, see if you can figure out exactly how this is working. If you don't, there's no problem. In fact, the actual PID controllers on the robot don't even use calculus anyway. So if you are curious about how these are calculated, it's actually really simple. You can ask me during the lab session. I can explain that just after we get started with things. But it's a useful thing to understand. So next we're actually going to look at how tuning a Limelight works. So this is the window that we see on the computer the Limelight's a camera on the robot, but we see this on the computer so we can tune it more easily. So this is, for example, a target that we're seeing right here. And what we're trying to do is make it so that the Limelight detects the target. One thing we can do is threshold it. So there's different values we can adjust. Typically, we won't actually do this. We'll use something called the eyedropper tool that tries to figure it out on its own. But sometimes the lighting changes at a competition. It's useful, rather than rebuilding the entire thing, just to make a few adjustments. So we have hue. That's one thing. We choose a range. And that's basically just a color. Every color is some kind of hue, nothing to do with brightness or darkness. Saturation basically is the range of how white or bright something is, and value is how much black is in that particular thing. These are just different things you can add to the threshold to help isolate the target from other things in the view. Erosion and dilation, not super important, don't apply to most situations, but if your target might have a hole in it, for example, someone ripped a hole in the tape or something and that's causing an issue, you could dilate it and that would just enlarge it a little bit so it could fill that kind of hole, make the target look a little bit better. Then we also contour filtering. This is going to be the other thing that you're going to adjust, probably more so. And there's a couple of things here, just looking at the target area. Like if the target's like this big on the screen, maybe it's not really the target, maybe it's just a false positive, so we can filter out those. And also target fullness. If you noticed in the last one how it was not actually a full rectangle, but just the sides and the bottom, it's actually, despite the area being pretty big, it's not actually very full. Whereas if it were a complete rectangle of tape, that would be a little bit different. So just another way of filtering. The last thing is target grouping. So you can see here we have multiple targets, and on our demo tape we also have multiple targets. So rather than just detecting one, we want to detect all of them. So there's ways of having this smart group that you can detect multiple targets as one. So now that we've looked at how we can actually make a pipeline, we're going to quickly go over how we interact with the Limelight on the robot. So we make a class and we call that our Limelight interface class. Very simple class. You can call it anything you like, really. I don't really care. This is just what we decided to call it. And all it does is it has two methods, a get tx and a get ty method. So tx is the degree error horizontally. So if I'm looking at the target and it's right over here, right, that's going to be one error. If it's too far, it's positive on the left side as well. And then ty is going to be the degree error up and down. And later we'll show you on the computer, that'll make more sense what those are. But basically it's just the horizontal for x, the how far off it is from the target, and y is the vertical, how far off it is from the target. So we have these two methods. They're almost identical, minus one difference. First, we create a network tables instance. So this is the first time we're looking at network tables as well. This is just very brief. You're not actually doing much with it. But network tables is the way we communicate with the Limelight on the robot. It sends it over Wi-Fi to us, and we can get these values directly on the RoboRio, which is the computer on the robot. So it sends all of this data through that, and it's in network tables. It has tables and entries inside of those tables. So we get a table. It's called Limelight. The Limelight automatically makes the table and sends you all the data. Then we get the entry for tx, or ty in this case down here. And then we get the double value. And if you remember, doubles are numbers with decimal places. So that means your error could be 10.5, 2.1, 1.0562, that kind of thing. And then the 0 here, all that does is that's the default value. So if there's no target, or it has never seen a target yet, it's not getting anything from the Limelight, it'll always return 0 then.
Question.
Yeah.
Can you have multiple Limelights on a robot?
Yes, you can. It's a good
question. If you do have multiple Limelights, how do you differentiate each Limelight in the tables?
Sure. So that's something you can configure on each individual Limelight. By default, the Limelight is the Limelight table. But if you did have two, you could give the other one a separate name in the configuration, and it would typically be Limelight dash something. So maybe it's Limelight for April tags in particular. It could be Limelight dash April tags, and it would be accessed the same way, just changing the table name. So next we're going to look at commands. So last week we touched briefly on commands. You made basic commands with the run and run once methods. Those are really simple. Today we're doing something more complex that requires more logic. So we're going to be looking at more like the whole idea of commands today. So commands are actions that are performed by the robot, right? We have different things: moving to scoring position, aim to target, for example, drive to goal. This is pretty old, but deploy mini-bots from an ancient game. But these are different actions that your robot can take. That's the kind of thing a command is. They store logic inside of them. So they specifically store how you want to accomplish your goal, and they interact with subsystems in order to do that. So to get sensor data, you would get it from a subsystem. To get the robot to drive, like to call the drive method, that's from a subsystem, right? Drive.drive%, something like that. So you control or get stuff from the hardware through the subsystems. Next, we're going to look at what a command actually is and how we structure it. So it's not as complicated as it sounds. First, we put them in a commands folder, right? Similar to how you had a subsystems folder. It goes up there, and we call it whatever the action is you want to take, then command.java. So aim to target command.java is the file. Then we can have our imports up here. We can create our different kinds of objects that we're trying to make. We take in different subsystems. As I said, that's how we control and interact with the robot on here. So we take in our subsystems right here. For example, it could be drive, and then the name of the subsystem could be drive as well, but that would be the type. Or maybe you have something else. You also would have to take in the Limelight interface there in your constructor. Then inside of here, you could initialize any of your variables from above and store your subsystems and other things that you need to store. This is the key though, these 4 sections right here. This is the key to a command. A command has 4 sections: initialize, execute, is finished, and end. So when you guys wrote run or run once, those are basically shortcuts for this. They do one of those in particular. So initialize sounds like what it is. It runs as soon as you start the command. So you press a button that's bound to the command. It calls initialize right away. Only once though when you do that. Every time you press that button, it'll do that. It'll run initialize once. Execute is run continuously every 20 milliseconds, right? Like every other loop that we do. And it's run as long as the command is running. So that's typically where we put all of our logic in. Is finished is a good place for checking if it's done. So if we have some specific condition where we want to end what we're doing, for example, if we're aimed at the target, like today, then we would return true to tell it that it's finished, and it would end the command for you. Otherwise, you would want to return false, and then it would keep going. Finally, once it ends, it calls whatever's in here. For example, maybe you want to stop the motors when it's done, something like that. Now, these should be familiar conceptually, but maybe you haven't heard the words before, because this is the same thing as run once. Run once is a command with just an initialize method, right? It just runs something once when you start it, and that's it. On the other hand, run is just execute. It's just a command with just an execute method, so all it does is repeat, right? So it's pretty similar to what you've already done, just gives you more control when you need more control. So here's how we're going to actually aim using the Limelight. It's pretty simple. First, we have to figure out what we're trying to aim at. So we get an angle back from the Limelight, and the angle we get back, what we're trying to aim for is up to us. Maybe you want it to be 10 degrees. For us, we want it to be aimed straight on, and so we want it to be 0 degrees, because that is right in the middle. Then, what we're going to do is turn the robot towards 0, using that tx value, that's how far off we are. And we're going to use PID and something called min speed, which is actually a feed forward, and we're going to use that to do it. And then finally, we will finish the command once we are within a certain tolerance of that error. Maybe it's not exactly on, but within some acceptable limits of what we're trying to get to. So let's actually look at how to do this. So here's our command, right? It's called our aim to target command. And we take in one subsystem right here, our drive subsystem, and we store it up there in a private field. We also take in a Limelight interface, and we also store that above here as well. Notice we also have a min speed variable. Like you've already seen with drive percent, that's a percent output that you would drive with. And we're just storing that for later. Then we create an angle PID controller. This is how simple it is. Remember, if it's PID, it goes PID. So we have 0 for these two. This is something you'll have to figure out on your own. Maybe it's not this value. It could be 0.3, 0.5, 0.01 maybe. And so this is your p-value right here. Then we have two pieces of configuration that we're doing. So this enable continuous input, not very self-explanatory, but basically what that does is it says, hey, our values loop around. So if our this is not necessary for this specific example, but it's typically a good practice that when you're working with angles can loop around. They can go from 0 to 360, but the PID controller by default wouldn't understand that. It would think that you've suddenly jumped by 360 degrees from where you just were, and it would go crazy. So this allows it to loop around to understand that those two things are actually the exact same. Then finally we set our tolerance. So we are converting this to radians. Not always necessary, but in this case, it works out well for what we're doing. So we're saying we're okay with being at most 0.2 degrees off. That's pretty tight. And you might not always be able to get away with that. But that's the tolerance we're saying. So we're saying don't stop until you're within that tolerance. Finally, we have a little method called add requirements. If you don't add requirements, it will not work. So you absolutely cannot forget that. What that does is it says, nobody else touch the drivetrain while I'm touching it, right? So by default, your default drive command is using the drivetrain. And if you don't do this, it'll keep using it. So you keep touching those controls and it will just keep driving on its own. So in order to say we are, like, this command is in charge of the drivetrain as long as it's running, you have to add these requirements. Otherwise it can be overridden and stopped in the middle, which we don't want. So next, let's actually look at those four methods that we talked about. Right? This is how the overall command works. This is our logic. First, we reset our PID controller. Let's say we were just aiming at something, and suddenly we start aiming again. If it thinks it was just where it was, maybe you drove in between, so it'll remember the last error from last time you were aiming, but suddenly you're in a completely different place. It's going to be confused. So you want to reset it before each time so it doesn't get confused. Then we set the set point. Set point is what I was talking about before. That's where you're trying to go. You're trying to go to 0 degrees or 0 radians. That's your set point. You could say something else there. Maybe you want to be a little bit off. That's up to you. Next, our execute. This is what we want to happen over and over again. This is the meat of the command. So our PID controller is called angle controller, and we call a method called calculate. We pass in our Limelight interface.getTX, right? So that gets that most recent x value, our most recent degree offset, like error, from the Limelight. It gets that, gives it to us. Then we convert it into radians, because it gives it to us in degrees. You don't have to do that. It just means your P will be a little bit different. And then finally pass all of that in. So we pass our error from the angle, we pass that into our PID controller. And it gives us an output of a double. That double, in this case, is literally just multiplying this value by P. If it were more complicated, it would do other things, but that's literally all it's doing here. So if our error were 0.1 and our p-value is also 0.1, then our output 0.01. 0.01. Pretty simple. The second part is also a little bit familiar if you guys have used math.copysign before as well. Basically, we have this min speed. Min speed, you could just not add it. It might work okay. But min speed is what we're calling our feed forward here. It accounts for friction. So the idea is your min speed should be enough for the robot to drive just a little bit, just so slowly, but that helps us not have to worry about something like friction. It means we'll always be able to get to where we're trying to go, even if we put just a little bit of voltage into it. So that's like, as I said before, our feed forward, and we want to put that in the same direction as our output, or else it'll counteract it, which could be a problem. Then our drive percent. We take in we put negative output and output. So if those were both output, it would just drive forward or backward, depending on which way we're going. But in this case, we want the robot to turn. And as you guys did before, to make it turn, you have to make sure both sides are not going in the same direction, right? So here we're having both not go in the same direction, which will make it turn. If it were a different robot, maybe the right one needs to be negative. That's up to you. But in this case, this is how we're going to make it turn at that speed. Then we're going to check if it's finished. The way we're going to know if it's finished is if it's at the set point. And remember, we set that tolerance before, so it's going to check if we're within that tolerance of our goal being 0. If that's the case, then we're finished. Otherwise, we're not. Right? So this is all built into the PID controller, which makes it really easy. Finally, at the end, we just want to make sure to stop the motors. You might not have this method. If you don't have that method, you don't need to call it. It'll probably be okay. But if you do have a stop method, you could use that as well, just to make sure you're safe. And then we're going to also talk about the other command that we're going to be making. So that was how to aim towards the target. This is how to drive to the target. Sometimes you need to be a specific distance away from your target to do something, not just be facing towards it. This is almost exactly the same, so I'm not going to spend a ton of time on every single section because you basically already saw this. Works almost the exact same as the other one. Instead of tx, we get ty, so we get a vertical offset instead of a horizontal. So why is that helpful? Well, if our Limelight is facing like this, right, it's looking like this, and our target is right here, right? So maybe if we're here, we want to be here. That's what the other command does. But this is also a y angle, right? So maybe we're -10 here. As we get closer, though, it gets closer and closer to 0. Maybe then it passes 0. So you can almost think of it like a distance. It's not exactly distance, but it's a shortcut. You can calculate distance, but we're not doing that today. But it will do the same thing it did before, but just drive to a specific height with ty. It's, again, similar to driving to a specific distance. We're going to use the exact same logic as before, though. So here, we can choose a ty that we want. So that's a difference, right? We're storing another field, a ty field. That's going to be the y value we want. You could just set that to 0. That's fine. But it's not as clear as just go to 0 for the angle. That's actually a distance you could set. So we want to make sure to store that. Other than that, also notice that our PID controller is 0.01, and our tolerance is a little bit bigger. In this case, we're not using this in radians. You could put it in radians. That's up to you. Most of this is the same. Notice our set point is our ty, our custom ty value now, the one that we want to go to, instead of 0, which it was before. We're not converting this to radians this time, but you could. It would work fine. And then our output is all the same. We are missing a negative sign there, though, because if you put a negative sign, it would spin instead of going towards it, right? So that's the key difference is we want to go forward or backward instead of turning like the other one. And then the is finished and end are exactly the same. Check if it's at the tolerance. If it is, stop the motors. So, time for lab, because this one's a lot. So let's look at what we're going to be covering today with the labs, because this is most of the work here. So we're actually mostly going to be starting on number 2. Okay, you're not going to be starting on number 1, and specifically you're going to start with making the Limelight interface. Okay, so you're going to work on the aim command first, right? The one where it aims towards the target, and we're also going to be tuning PID values with that. You're going to start by writing that code. We're going to take you guys one at a time. Anshi's going to show you how to actually make the pipeline, and then you can go back to coding. Right? We're just going to take everyone through how to do that while you're working on the code. Once you're ready to test, you can test it with the actual cardboard target that we have. Make sure that you remember how to bind the command to a button as well. Then, if you finish that, you can create the drive towards target command, and that is pretty much the same as I discussed. If you are done with that, which of course, as always, you don't have to, right? And specifically with this one, it's very possible you don't finish all of them today. That's totally fine. It's a lot. If you are done with that, you can combine them. So you can make one command that actually does both. It drives towards the target and aims at the same time. So that's your optional one for today. And if you have any questions, obviously let me know. This is your QR code for the presentation so that you can look at that. And we're going to get started.